You know all the numbers you use every day? Ones, twos, fractions, decimals? Have you ever stopped to think about how they all fit together? Like, is there a master system for organizing every single number you can possibly imagine? Well, there is. And today, we're going to build it. We're going to create the complete number line and put every number in its proper home. Let's jump in.
So here's our game plan. We'll start by sorting numbers into different groups. Then we'll dive into the world of rational numbers and see just how crowded it is. After that, we'll uncover some mysterious numbers hiding in the cracks, the irrationals. We'll even figure out how to find them on a number line. And then we'll wrap it all up with a super quick summary of the key things you gotta know.
Okay, so to get our heads around this, let's imagine we've got a bunch of bags, one inside the other, kind of like Russian nesting dolls. Each bag is for a specific type of number. Our mission is to sort every number we know into the right bag. It's a really simple way to see how all these number types are related. So let's pack our first bag.
First step, we have the most basic, natural numbers. We call them the natural numbers and we label the bag N. These are just your good old-fashioned counting numbers. 1, 2, 3, 100, a billion. You get the idea. They're the building blocks for everything else.
Now we take that whole N bag of counting numbers and we drop it inside a slightly bigger bag. This one is labeled W for whole numbers. And what's the big addition? What makes this bag bigger? Just one single number. 0. That's it. Whole numbers are just all the natural numbers with 0 thrown in for good measure. Time to expand again. We're going to take our W bag and put it inside an even larger bag labeled Z for integers. Now this bag has everything we've collected so far, plus all of their negative opposites. So -1, -2, -1,000, they all go in here. Suddenly, we can talk about things like temperatures below freezing or being in debt. Pretty useful, right?
And now for the biggest bag we've seen yet, the one that holds all the others. This is the set of rational numbers, which gets the letter Q. Now the official exam-ready definition is this. A number is rational if you can write it as a fraction, P over Q, where P and Q are both integers. But there's one mega important rule. Q, the number on the bottom, cannot be 0. You just can't divide by 0. This bag includes all the integers, plus every single fraction and decimal you've ever met.
So we've got all our integers and now all the fractions in between them. You'd think our number line must be completely full now, right? I mean, if you pick any two numbers, can you always squeeze another one in between them? Let's find out.
Here's a super slick trick for finding a number between any two other numbers. It's called the mean method. You just pick two numbers, let's say 1 and 2. Add them up, you get 3. Divide by 2, and you get 1.5. Bam! There's a number smack dab in the middle. And here's the crazy part. You can do it again with 1 and 1.5, and then again and again forever.
But you know, finding the average over and over is kind of slow if you need, say, 5 numbers between 3 and 4 all at once. There's a much faster way. It's the n+1 method. If you want to find n numbers, you just give both your starting numbers a common denominator of n+1. So to find 5 numbers, we'll use a denominator of 6. We rewrite 3 as 18 over 6 and 4 as 24 over 6. And look, the numbers in between just pop right out. 19 over 6, 20 over 6, all the way to 23 over 6. 5 numbers, just like that.
So here's the big takeaway. This is absolutely crucial. Between any two rational numbers you can possibly name, no matter how ridiculously close they are, there are still an infinite number of other rational numbers. It just seems like the number line has to be completely jammed packed.
Okay, so an infinite number of points sounds pretty complete, right? You'd be totally right to think the number line is full. But here's the plot twist. Even with infinity packed in there, the rational number line is filled with microscopic, invisible holes. There are secret numbers hiding in the gaps.
Let's think about this little equation. X squared equals 2. So what number, when you multiply it by itself, gives you exactly 2? Well, it can't be 1 because 1 squared is 1, and it can't be 2 because 2 squared is 4. So the answer has to be somewhere in between 1 and 2. But the real question is that number, the square root of 2, a rational number?
When you actually try to calculate the square root of 2, something really weird happens. The decimal part just keeps going. You get 1.4142135 and on and on and on forever. And here's the kicker. The digits never end and they never ever fall into a repeating pattern. Now, think back to our definition.
A rational number's decimal either stops or it repeats. The square root of 2 does neither, so it simply can't be a rational number. And that leads us to a whole new bag of numbers, the irrationals. These are the rebels, the numbers that you cannot write as a simple p over q fraction. Their claim to fame is that their decimal expansions march on to infinity without ever repeating a pattern. Some of the most famous ones are the square root of 2, the square root of 3, and of course the absolute superstar of irrational numbers, pi. Speaking of pi, here's a really fun fact for you. We celebrate Pi Day on March 14th, that's 3/14, because the first 3 digits of pi are, you guessed it, 3.14. And get this, in what has to be one of the coolest coincidences ever, March 14th is also Albert Einstein's birthday. Just like root 2, pi's decimal places go on forever with no pattern, which is why it's irrational.
So let's just put it all side by side. It really boils down to the decimals. If the decimal part stops or repeats a pattern, it's rational. If it goes on forever and never repeats, it's irrational. That's the test. They are two totally separate teams of numbers. A number can't be on both.
So what happens when we take our huge collection of rational numbers and we dump in this new collection of irrational numbers? What do we get? We get the whole shebang. The complete set of real numbers, marked with a capital R. This is the master set, the final bag. And when you put the rationals and the irrationals together, they finally fill in all the gaps, giving us a perfect, seamless, totally complete number line. Okay, so it's cool to know these irrational numbers exist. But how on earth do you actually find one, like the square root of 2, on a number line? I mean, you can't just measure it out. Well, it turns out you can pinpoint its exact location with some pretty simple geometry. This is actually a beautiful little construction you can do yourself. You start at 0 on your number line, and you draw a perfect square where each side has a length of 1. Now, thanks to our old friend Pythagoras, we know that the diagonal of that square has a length of exactly the square root of 2. So you just take a compass, measure that diagonal, then swing it down onto your number line. And where it lands, that's the exact, precise spot of the square root of 2. And what's really amazing is you can just keep going. You can take that new length, the square root of 2, make it the base of a new right-angled triangle, and if you make the height 1 again, the new diagonal will be the square root of 3. Do it again, and you get the square root of 4, then 5. This process creates this incredible, beautiful image called the square root spiral, which is basically a visual proof that all of these weird numbers have a perfect home on the number line. But what about finding a number with a long decimal? For that, we use something called successive magnification. It's basically like using Google Maps on the number line. To find 5.28, you first look at the big street between 5 and 6. Then you zoom in to find the smaller block between 5.2 and 5.3. Zoom in again, and you'll find the exact house, 5.28. You can keep zooming in forever, which means that even a number with infinite decimals has a unique, precise address on our line. All right, we have been on quite a journey through the universe of numbers. So let's take a second to lock in that knowledge and do a super fast recap of the things you absolutely have to remember. Just remember those nesting bags. Naturals live inside wholes, which live inside integers, which live inside rationals. And then the rationals and the irrationals come together to create the set of all real numbers. The big difference? Rationals can be written as fractions, irrationals can't. And when you put them all together, you get a perfect, gapless number line where every single point is a unique real number.
Okay, theory's one thing, but now it's time to put what you've learned to the test. I'm going to throw some questions your way. I really recommend you pause as we go and try to solve them yourself.
Let's start off with some easy ones, just to get the brain warmed up.
All right, take a look at these. How about number 1? Is 0 a rational number? Well, remember the rule. Can you write it as p over q? Sure, you could write it as 0 over 1 or 0 over 5. So yes, it's definitely rational. Or how about number 9? Is pi equal to 22 over 7? That's a classic trick question. The answer is no. 22 over 7 is just a convenient rational approximation of pi, but it's not the real thing.
Okay, nice job. Let's crank up the difficulty just a little bit with some application questions.
These are going to make you think a bit more. Take a look at number 1. Finding 3 numbers between 1/3 and 1/2. That's a perfect time to use that n+1 method we talked about. And number 9 is a great one. Are the square roots of all positive integers irrational? What do you think? The answer is a big no. Just think about the square root of 4. That's 2. Or the square root of 25. That's 5. Those are integers, which means they are definitely rational.
And now for the final boss round. These questions will really show if you've mastered these concepts.
Let's look at number 10, a real mind-bender. Express 0.999 repeating as a fraction. We know it has to be rational because it repeats, but when you do the math, you get the surprising answer that it's exactly equal to 1. How cool is that? And look at question 3, a brilliant conceptual trap. Kruji says root 2 can be written as root 2 over 1, so it fits the p over q form. Is she right? Nope. The definition clearly states that p and q must both be integers, and the square root of 2 is not an integer. Getting that right shows you really truly understand the rules.
And we'll end today with this incredible thought from the legendary Indian mathematician Srinivasa Ramanujan. It's just a beautiful reminder that behind all these rules and lines and numbers, we're really just exploring the elegant underlying structure of the universe itself. So keep exploring, stay curious, and you'll be amazed at what you find. That's it for now.